So in this lecture, we're going to continue our discussion of pericyclic reactions, moving into the next example of a pericyclic reaction, the sigmatropic rearrangement. So the sigmatropic rearrangement is, it's important to kind of categorize this as a rearrangement, so a reorganization of the bonding pattern within the molecule. It's not like a cycloaddition or a ring formation reaction. And so with that in mind, what is the sigmatropic rearrangement? Well, in a sigmatropic rearrangement, what you do is you convert a sigma bond to a pi bond and a pi bond to a sigma bond. So at this point, it's not obvious where the thermodynamic driving force comes from, whereas in the previous reactions, we talked about the energy kind of potential, that the energy that was released as we formed sigma bonds at the expense of weaker pi bonds. And so let's look at an example of this. So the most basic example is the 3,3 sigmatropic rearrangement. So in the 3,3 or 3,3 sigmatropic rearrangement, we're going to take a, that's a little iPad sloppy there. Let me do better. Okay. We're going to take a 1,5-hexadiene. And in this 1,5-hexadiene, we can apply heat or light to sort of force the equilibrium to occur where these two structures intermix with each other. Now, it's important to note that the reactant and the product here are degenerate. Or for all practical purposes, the same. Now, what degenerate means is of the same energy. And so the big KEQ is equal to 1 here. Concentration of products over reactants is equal to 1. We don't have a thermodynamic driving force here, but at least we can see a 3,3 sigmatropic rearrangement occurring. Now, what does this reaction actually do? Well, it takes pi bonds at the end of our molecule. We're going to use one pi bond to make a new sigma bond and then push the other pi bond over to make a new pi bond, a new double bond, but also break a sigma bond. And these arrows, again, sort of look all the same, but with a different type of bonding pattern to start with, you get a different outcome. And so here, if we're careful, we can get the same molecule out as what we started with. So it's a pretty cool transformation. We could flip back and forth in either direction. What's important about pericyclic reactions, I don't think I've emphasized this at all, but it's an important note, is the arrows can actually go about in either direction for the reactions to occur. Now, sometimes with dipolar cycloadditions and charged dipolarophiles, it makes more sense to have the negative charge at one end and the arrows starting there. But for most cases, particularly with all carbon systems, you can draw the arrows in either direction and then get to the same outcome. So in this case, we don't have a thermodynamic driving force, but at least we can see a representative transformation occurring. Now, this leads to an important name reaction, which is the Cope rearrangement. Now, the Cope rearrangement is an example of a sigmatropic rearrangement. But in this case, we're going to take advantage of an important transformation that we all have seen and at least been tested on, which is keto-enol tautomerization. And that's going to serve as our thermodynamic driving force to get to one side of the equilibrium in our sigmatropic rearrangement. So that has a thermodynamic driving force. Okay, so the reaction is thermodynamically driven to one side of the equilibrium, and it's just taking advantage again of Le Chatelier's principle. So what we're going to do here is initiate our equilibrium to occur between our two hexadiene motifs. Now you'll notice that I have my 1,5 hexadiene again, and I'm once again going to do a 3,3 sigmatropic rearrangement, which I show in brackets. Now what does that mean? Okay, so I'm going to take my hexadiene, I'm going to draw the 3 arrows to give rise to the product of a sigmatropic rearrangement. Now before we didn't have that OH, and so the product and the starting material look the exact same. Now here that's not the case, so the equilibrium is not going to perfectly be, the equilibrium constant, is not going to be perfectly 1, but let's not worry about what it is, because the product, our alarm should be going off in our head, we've got enol radars that allow us to recognize that when an enol is formed, we're going to allow for tautomerization to occur, a process that can be facilitated by a small amount of either acid or base and catalyzed by those two species. So it doesn't, as long as we got something around and some, we can induce this. We can induce this tautomerization process to occur. Now what that looks like is, in this case, the enol is stretched out across the OH. So this is kind of a clever trick by Kobe to position the OH such that after the sigmatropic rearrangement occurred, we could have the formation of an enol, which would spontaneously tautomerize to an aldehyde. Now the aldehyde exists as our thermodynamic resting state. That is, the equilibrium, we can start the reaction with all starting material, and that starting material can equilibrate back and forth across the sigmatropic rearrangement equilibrium to get to either product. But once we achieve the formation of the enol, some amount of the enol will, for the most part, irreversibly be pushed forward onto the aldehyde. That's going to perturb the equilibrium from the sigmatropic rearrangement, siphoning away product. To make up for that, we're going to reestablish equilibrium by driving a greater concentration of starting material over until eventually all of the starting material is for the most part consumed, except for maybe like a trace amount that exists in microscopic reversibility. As we say, just a small amount went backwards from the keto to enol tautomerization. But regardless, for the most part, the majority of the material for our eyes will be the aldehyde in the reaction mixture. And so what we can do is just sort of recognize an interesting opportunity that the sigmatropic rearrangement provides for us. We could generate enols and ultimately give rise to carbonyls. And this is a really popular reaction for generating important functional groups, because anytime you can kind of play with a carbon skeleton like this, you can get to some really interesting structures. And so how would you make these, for example? So an approach, and let's specify, how do I make this? Well, one particularly interesting approach that led to a really, ultimately led down a rabbit hole to a really interesting discovery was if you had, for example, acrolein, you could add to that some sort of R metallic, and let's actually specify what the R group is, and let's not worry about what the metal is. I'm just showing you an approach where the metal is off of an allyl system. So you could imagine maybe making a Grignard, making an organolithium, and you're going to get sort of a mixture of products, but this just shows you an interesting approach to making these things. Now, if we sort of streamline the mechanism a bit and just consider the electrons from the carbon metal bond adding directly to the carbonyl, that's going to push the electrons up. And again, this molecule that I've shown here is acrolein. It's not a friendly chemical, but it's a readily abundant chemical. So it's pretty dangerous aldehyde. But anyway, I mean, you can get access to it if you need to do some chemistry on it. You just don't want to inhale it from cigarettes, which happens quite a bit. Anyway, neither here nor there, I guess. So that would give rise to our desired product. Now, coupled to a metal ion. Okay, so at this point, we just need to protonate right and get right to the product of the reaction, right? I mean, if we protonate this, we can go right to the product that will give rise to the aldehyde by way of a sigmatropic rearrangement and a keto-to-enol tautomerization, as I have listed up above. Now, what's really cool about this is you can't really protonate this species and hope to get that precursor to the cope rearrangement keto-to-enol tautomerization cascade. Instead, what happens quite remarkably is this has a K-rel, and that's a little k. I mean, it's a lowercase k. I know it's drawn big. We're going to put a K-rel here equal to 1 times 10 to the 17th. Now, that's a really big number. Now, what does that number mean? That means that if you compare this to the background parent reaction, it is 1 times 10 to the 17th faster. That is to say that this has a K-rel equal to 1. So if the protonated species reacts at some rate constant, I don't know, let's call it 2 and then rate constant units, okay? If you have the deprotonated version, this will undergo a with a rate constant of 1 times 10 to the minus 17th. This will undergo a very rapid reaction. Whoop, I already drew it wrong. Where you get this species, and that's through a 3,3 sigmatropic rearrangement. And then if you have your H plus, you're going to see this form the carbonyl product, and you could draw arrows from the resulting enolate intermediate. Okay, let's summarize these thoughts and attach a name to this. This is called the anionic cope rearrangement. So it's a cope rearrangement. The difference is that we're starting with an oxyanion. That is to say, the alcohol in the parent cope rearrangement is deprotonated to form an oxyanion. Just an alkoxide is all that is. But it turns out that the alkoxide has a rate constant for the 3,3 sigmatropic rearrangement that is 1 times 10 to the 17th. 1 times 10 to the 17th greater, and by greater I mean faster, than the parent reaction. Now, we've done a lot with charge in our 2.5 semesters together studying organic chemistry, right? Or yeah, 2.5 semesters. We've done a lot with charge, you know, and dipoles and that sort of thing. But if we look at this mechanism, that is to say, it's my sigmatropic rearrangement mechanism. Whether or not I've got a negative charge there doesn't really influence where the arrows are going, right? Whoops, I just drew the same product. Got focus. Like the curly arrows are not directly, oh my gosh, I'm so sorry. Wake up here. Okay, I'm going to focus on this. I'm going to draw the bond close there. All right, there we go. The arrows are not directly kind of driven by the negative charge that's present in the molecule. It's just a negatively charged oxygen atom that's in conjugation with the product, but not the starting material. And I'm not talking about thermodynamic stability here, okay? Because we could draw a resonance structure in either case where we delocalize electrons from a lone pair on oxygen into the pi system from that enol product. We can do that in either case. And again, I'm not worried about the equilibrium. I know I'm drawing the equilibrium arrow such that the equilibrium constant is 1. I'm just worried about the speed. 1 times 10 to the 17th faster without electron density that obviously is impacting the arrows at all. The arrows are the same. I don't know. It's just one of those mysteries. Not mystery is a strong word. It's just one of those observations in chemistry that really kind of gets you fired up because you're like wow, okay, that's just a really impressive transformation. Okay, what I want to do now is I don't want to make the sigmatropic rearrangement lecture too long, so I'm going to break there because that's long enough. Then we'll look into other types of sigmatropic rearrangements. I guess before I go, let's just do the Claisen rearrangement, and then we'll call it a lecture and move on to more sigmatropic rearrangements next time. So the Claisen rearrangement is another one that takes advantage of an interesting tautomeric equilibrium. Okay, so in this case, we're actually going to position an oxygen within the system that's within the atoms as an atom that's participating in the sigmatropic rearrangement. So here we could have, and let's just draw this a little bit more generally. So we could do a sigmatropic rearrangement like this. So this is going to be another 3-3 sigmatropic rearrangement, except for an oxygen built in. And this is not a Cope rearrangement, but instead this is a Claisen rearrangement. And here, so in this case, it's likely the case that we're going to see this equilibrium be favored towards the product where we have a carbonyl. So that's what's kind of cute about this reaction, is you form a carbonyl in the product. Okay, now let's look at a specific example. I think I got this from the book. So we're putting the oxygen at the system of our, within the system, within our 1,5-hexadiene system. But now the example from the book is that one of the alkenes is actually part of an aromatic moiety. That is, it's part of a benzene ring. So we have a phenol allyl ether. And if you apply heat to this reaction does not have as strong of a thermodynamic driving force, at least initially, because we have to break aromaticity for this reaction to occur. But what we can do is we can push this towards a tautomeric equilibrium that's favorable because we re-aromatize our product. And after we re-aromatize our product, we're no longer able to do a 3-3 sigmatropic rearrangement with the same kind of driving force that we had initially. That is, if we do the 3-3 sigmatropic rearrangement again, we'd have to first tautomerize out of aromaticity as opposed to rearranging out of aromaticity. So we'd have to do a tautomeric, we'd have to achieve tautomeric equilibrium at to put the hydrogen back at this position. It's just not favorable. So this reaction is driven towards an aromatic enol tautomer. But what's interesting is it's from an aromatic enol tautomer. So these reactions are just, in my view, they're a little tricky at first because you don't have charge and that sort of thing to direct your eye. But I think in the long run, these reactions can be really fun, especially ones that rely on some sort of tautomerization at the end of the day to get to a thermodynamic driving force. But yeah, anyway, as promised, I'm going to call it this lecture. We'll look at sigmatropic rearrangements in more detail in the next lecture.